Hi everyone, welcome to week 3. I hope everyone had a great weekend. So today we'll be talking about non-parametric few-shot learning. But before we talk about that, a few logistics for the class. First, on Wednesday, homework 1 is due. So hopefully you've been able to make some progress on that. And then we'll also release homework 2 on Wednesday. On Wednesday, the project survey is also due. This isn't binding, but really the goal of this is for us to get a sense for who your groups are so that we can assign a TA as a project mentor or a point of contact. And that TA will essentially be the person that can help you out with, answer questions, that sort of stuff. And kind of by default, you should be going to your TA mentor's office hours once you get assigned a TA mentor. If you don't fill out the project survey, then we won't assign you a TA mentor until you submit the project proposal. On Thursday this week, we also have a tutorial on variational inference, and the goal of this tutorial is to help potentially prepare for Monday's lecture next week, which will be on kind of advanced Bayesian meta-learning methods. And if you're already familiar with variational inference, then you shouldn't feel like you need to go, but I think that it should be helpful for understanding Monday's lecture. And Monday's lecture is one that will dive a little bit deeper than some of the other lectures, but I think that it will also, in some ways, give you a better understanding of meta-learning algorithms. And then next week, the project proposal is due on Wednesday, and so you should be starting to think about what you're doing for your final project. And in general, these proposals are they're graded very lightly. Really, the goal of the project proposal is to help you kind of have a milestone for understanding what your project is going to be. And so really these are just for your own benefit, and the grading is also for your own benefit to help us give you feedback on your project proposal. And then also next week there'll be a tutorial on value-based RL, which will help prepare for some of the RL topics that we're getting into next week. Any logistical questions? Okay. Cool, so the plan for today, we're going to be covering a class of methods called non-parametric few-shot learning methods. These methods are actually work super well in practice, at least for supervised learning problems, and so they are quite useful. We'll also talk about a case study of using these methods in actual kind of a real-world deployment of meta-learning, which is pretty cool. Then we'll summarize the different meta-learning algorithms that we've covered so far, including non-parametric methods, and discuss their pros and cons. And then I'll end just by giving a few examples of some more meta-learning applications and how these algorithms have been used in practice. The goals by the end of the lecture are to kind of get the basics of non-parametric few-shot learning and how to implement them. And you will be implementing them within homework 2. Also trade-offs between the different meta-learning approaches, and then familiarity with kind of more applied formulations of meta-learning and how you can take a problem and formulate it within the context of meta-learning. Okay, so before we dive into non-parametric methods, just a quick recap of what we covered last week. We talked about first black box meta-learning methods, which essentially have a neural network that take as input a training data set and output some parameters or output some sufficient statistics, and then those parameters are used to classify new data points. So really the key idea is to parameterize a learner as a neural network, where this learner is going to be taking in data points directly. This was great in the sense that it's a very expressive process. You can represent many learning procedures, and the downside is that it's a fairly challenging optimization problem, and this might be something that you're finding in homework 1. Okay, and then we also talked about optimization-based meta-learning, and instead of representing the learning process as a black box neural network, we instead represented it as an optimization process where we meta-learn the free parameters of that optimization process. And so one instantiation of this is you embed gradient descent into the inner learning process. And the benefit of this is that you get the structure of optimization embedded inside the meta-learner. And the weakness is that it typically requires some sort of second-order optimization. Now, one thing that I like to emphasize in both of these approaches is that really the only thing that you're optimizing per se in both black box meta-learning and in optimization-based meta-learning is the parameters theta. In some ways, phi I is just kind of an intermediate byproduct of this meta-learning process, and it's not being actually optimized as part of meta-learning. It's something that you're essentially inferring at test time in order to solve the task. Okay, any questions on this kind of material from last week before we move on? Okay, so these optimization-based approaches typically require some form of second-order optimization, which makes them, is one of essentially the main downsides of these approaches. And so today, essentially, we want to be able to embed a learning procedure and get the structure of an existing learning procedure without requiring a second-order optimization. And so this is really the motivation behind nonparametric methods. And essentially, so far, we've been learning we've been using nonparametric models. We've been using models that are parameterized by phi I as the kind of ultimate product of the learning procedure. However, in low data regimes, nonparametric methods actually work pretty well, and they're quite simple. So for example, nearest neighbors is one possible nonparametric learning procedure where you don't actually necessarily have any parameters. You are trying to compare examples to the nearest training data point and output the corresponding label. This gets really expensive when you have a ton of data points, but when you have a small number of data points, you can simply compare the example that you have to all your training data points. And so for this class of meta-learning methods, we can notice that at meta-test time, we are in this low data regime oftentimes when we have a few examples, a small training data set. That said, during meta-training time, we still want to be parametric because we will hopefully have a large amount of data that we can use for the meta-training process. And so the idea here is, can we use parametric meta-learners that produce effective non-parametric learners? Okay, and it's also worth mentioning that some of these methods, in terms of when they're introduced, actually precede the approaches that we've covered so far. Okay, so what exactly do I mean by using a parametric meta-learner to produce a non-parametric learner? So let's think about nearest neighbors as our non-parametric learner. And what it's going to look like is if we have a training data set at test time and a test data point, we're just going to compare the test data point to each of the training examples. So we'll run a comparison between each of these, and we'll find the one that is closest to our target image and output the label of the corresponding image. So we're just going to be comparing the test data point with our training images. Now, an important question is, well, in what space should you compare between the test image and the training images? One really naive option that you could do is to use L2 distance in pixel space. However, this turns out to be actually a really bad metric. So if, for example, you take, say the image on the right is your test example, and the two images on the left are what you're comparing against. If you compared to these two images, nearest neighbors, L2 distance in pixel space will actually tell you that the image on the left is closer than the image on the right. And so this illustrates essentially why L2 distance can be really terrible. In image space, it can also be terrible in other spaces as well. So we probably shouldn't use L2 distance in pixel space. Does anyone have any ideas for distance metrics that we might use instead? Yeah?
We could run like a RedTrap on like ImageNet and then
so we use features from a model trained on ImageNet. Any other ideas? Yeah?
So train a self-supervised model.
You could also use a model that was trained in a self-supervised way instead of something that's trained in a supervised way. Any other thoughts? Yeah.
Contrastive learning, I guess, also self-supervised, but like taking out some augmentation, kind of match images that are like similarly augmented and increased distance for different images, something like that.
Yeah, so you can try to do some sort of contrastive learning that essentially pulls together images that have a similar label and pushes apart images that have a different label. And you could do this either in a labeled setting. It's fairly easy to do this. You could also do it in an unlabeled setting potentially if you have if you make certain assumptions. So all these are kind of examples of actually trying to learn a distance metric in various ways. And the key idea behind kind of non-parametric few-shot learning methods is to actually learn a metric like this, except learn a metric in a way that is explicitly optimizing for good performance at this meta-test task. And so we want to essentially use the meta-training data to learn how to compare images. Now, a really simple way to do this is very similar to like a contrastive technique, where essentially what we'll do is we'll just train a network to take as input 2 images and output whether those images are the same class or not. And so if these are different classes, you train it to output a 0. If they are images of the same class, like they're both images of bowls, you train it to output a 1, and so on and so forth. You essentially pass in these pairs of images and train it to output whether or not they're the same label. And this is essentially going to look a lot like a contrastive learning approach. Great, so this is essentially the basics of a non-parametric meta-learning method. This is referred to as Siamese neural networks. And then once you train a network like this that tells you whether 2 images are from the same class, then at meta-test time, you simply compare x-test to each of the images in your training data set and output the label corresponding to the one that you're most confident is the same class. Yeah?
So in this context, non-parametric just means that we're not creating or optimizing parameters at testing time, even though we are still using parameters at testing time.
Yeah, so the question is essentially, does non-parametric mean that we're not using any parameters we're not like kind of creating a classifier with parameters at meta-test time, but we're still using parameters in this process, and that's exactly right. Yeah?
So the Siamese network that predicts if 2 images are in the same class, is that like trained separately before the meta-learning process, or is that trained along with the meta-learning process?
So this training the Siamese network directly corresponds to the meta-training process, essentially. And then at meta-test time, you deploy that classifier to run all these comparisons. Yeah?
These non-parametric, let's assume that we have the same labels.
So that you're asking, it assumes that we have the same label space between training and testing? Yeah, so this is specific to classification. And it's assuming that you're going to be doing some Endway classification problem at meta-test time, and that your meta-training data is labeled with class labels. Oh, that's a good question. So do the meta-test classes have to have the same class labels as what you saw during meta-training? And it doesn't actually have to have the same class labels. So this is actually a binary classification problem right here. And it's just telling you whether or not they're the same class. And so if you then give it images of new classes, of images from entirely new classes that weren't seen during training, the classifier should still be able to generalize and tell you whether or not they're the same class. And so you don't have to have the same class labels during meta-training and meta-test time. OK. Great, so this is like V0 of non-parametric few-shot learning techniques. And at meta-training time, you're doing this binary classification. And at meta-test time, you're doing an Endway classification by running these pairwise queries or comparisons. Yeah?
With meta-testing, it's steadily going to compare the images with each image the training data, not the test data. But wasn't that realized that you don't want to just testing the training data while you're testing?
Yeah, so I should clarify. You're comparing it to each image of the support set or the training set of your test task. And this is separate from your meta-training data. So you'll use all of the training tasks, all the kind of meta-training tasks that you have to train this binary classifier. And then at test time, you'll be given a new task and a small amount of images, of training images for that new task from new classes. And you'll be running comparisons on that small amount of labeled data. Yeah?
So just that during meta-test, we just compare the test data point with each data in the training data set. So would it be very complicated in testing? I mean, if you increase the number of classes in the training set and significantly doing meta-test will increase median as well?
Yeah, so the question is, does this get very expensive if you have a very large support set of your test task, a very large training data set for your test task? And yes, it does get very expensive. It will increase linearly as the size of your training set grows. In few-shot learning scenarios where we only have a few training examples at test time, it's still very practical to run. But if you have, if you want to meta-learn a task that has a large amount of training data per task, this might not be the best approach. Yeah.
Oh yeah, so just to clarify, I guess here in meta-training time, we don't have any task structure, right? It's just a bunch of paired kind of images going together and learning how to see.
Yeah, exactly. So I guess the question is, there isn't actually any explicit task structure during the meta-training process. And that's right. We'll actually see in the next approach that we'll actually leverage the task structure more explicitly. But here you're actually kind of breaking down the task structure and just using the classification labels. Yeah?
And if I gave you 2 shots now, that would give any advantage, right? Test learn.
Good question. So what if you had more than one example per class? You had 2 shots per class, for example. Does that give you any advantage? So I guess, does anyone have any thoughts on this question? Yeah?
And you can take the 2 shots independently and then you average the answers, you roll it. That's like if you wrong because of like noise or that are more likely to be close to your expected test performance of this specific task that's cool. And but for the question before, I don't think it's similar to breaking down the task structure. Because for example, if every training data set has different labels, like for example, the line will never appear in the middle of the task like this one, then like you still have distinct tasks and you cannot treat this. You cannot compare like, images across tasks.
Yeah, so I guess there's 2 things here. In terms of the task structure, you're essentially making the tasks just be binary classification tasks during meta-training. So there is sort of that structure in that you have a binary classification task. But going back to the number of shots question where you have multiple data points, there are a few different ways that you can handle this. The naive way to handle it is just to treat the shots independently from one another. And you still do get a benefit from having multiple shots in that case, because if it's closer to one of them than the other, for example, then it will actually still output that label. And so you still do get benefits from having multiple shots, even if you treat them independently. That said, there are better ways to handle multiple shots that we'll handle in the next couple of slides. Okay. So one thing that you might notice here is that meta-training and meta-test time, they're doing different things. And one of the things we saw in the previous lecture is we often want to kind of match what we're doing, what we're training for at meta-training time, and what we're ultimately going to be doing at meta-test time. And so we want to create a procedure that actually matches what happens at meta-training and meta-test time. Now, the way that we can do this is instead of doing binary classification during meta-training, we can actually do Endway classification, doing nearest neighbors in some learned embedding space. And what this will look like is this diagram right here, where each of our training examples, say we're doing 4-way classification, each of our training examples are here. We compute an embedding for each of those 4 examples. And then we do nearest neighbors with our test example in a differentiable way, such that we output the label corresponding to the thing that we're closest to. So in this case, maybe it decides that the weight for this example is the highest, and so we'll output essentially a softmax distribution over those weights. And so in particular, mathematically, what this looks like is we will compute embeddings for each of the examples, and then we'll compare them using essentially this network. We're essentially going to be computing the similarity between each of the training examples and our test example. We'll look at each of the label for each of those corresponding training examples. And then we will have y-test correspond to this dot product between the weights and the corresponding labels. In terms of the architecture, there's a number of details that you can do here. This architecture uses a convolutional encoder for the images. It also uses a bidirectional LSTM so that the embeddings of each example doesn't just depend on the example itself, but also depends on the other examples. But those are essentially more sophisticated choices that you can do. But really the key idea here is that if we train this end-to-end, then we can actually train for nearest neighbors in Endway classification to give you the right answer, rather than training for this kind of the binary classifier on the previous slide. Yeah.
The neighbor matching in a differentiable way, we need something like attention, or like how do you do it? Like that.
Yeah, so it essentially looks a lot like attention. Attention is essentially just a dot product. It's like a really fancy way to say that we're going to be doing dot products, and you can see it like essentially what looks a lot like a dot product right there, where we're going to be computing this similarity metric between the test example and each of the training examples, and then according to that equation there, taking that similarity function, multiplying it by the label, and then summing to get a distribution over labels. Yeah.
One thing I was thinking about the previous method is that it's really dependent upon the training data and how similar the classes are in the training data. And it seems like this potentially fixes that like reliance on data because you're getting them all at once. Or it's like I don't know if I said that correctly, but right in the first one, you have things that are very similar but in different categories because you have very similar categories. That could really mess you up, but this one might be able to correct that because it understands when things are similar to begin with because it gets them all at once.
Yeah, that's a great question. So essentially the question is that if you have some classes that are more fine-grained than others, then the Siamese classifier, it doesn't necessarily know for a given class if it's like a very fine-grained class or not a very fine-grained class. And then when you do comparisons only pairwise, it has to essentially guess how fine-grained the class is or not. But in this case, you're actually passing in the entire, like all of the classes into the network. And this allows the network to actually look at what the other classes look like, realize that they're breeds of dogs and not dogs, for example, like dogs versus cats, and use that to determine how fine-grained of a comparison it wants to do. And so looking at the entire, like all of the classes in the problem actually allows it to tailor how narrowly it will be defining a class. Yeah.
Can we suggest number where input is from some low-dimensional space?
So I think the question is that what if it's not images, what if these are low-dimensional data points? Yeah, so certainly you can essentially, this is an image classification example, but you could also do other classification problems where this corresponds to like text, or maybe it corresponds to tabular data or something like that. And you probably wouldn't use a convolutional network if it's like tabular data or something like that, but you can use the same sort of idea. Yeah, the main ideas will still apply. Yeah.
What is the goal on the LSTM? Couldn't they find some form of ordering function?
Yeah, that's a great question. They used an LSTM here, and it does actually impose some form of ordering, which isn't a great design choice. It would probably be better to use an encoder that doesn't actually depend on the order, like attention and so forth. This was back in 2016, and so things like transformers weren't as popular back then. Or I think the transformer officially didn't really exist back then. And LSTMs were one of the more popular things to operate on sets. But it does impose an ordering, and there are probably other architectures that could try to take into account all of the information of the training data points without imposing an ordering. Yeah?
Out of curiosity, I'm wondering how this kind of meta-learning approach compares to taking, like, let's say a lot of images at training time and then choosing fewer classes at test time.
So the question is, like, what if you take a lot of classes at training time and then fewer classes at test time?
Yeah, like without like all this
Yeah, so one of the things that's important here is if you want to be able to generalize to new image classes that aren't in your set, the set of things that you saw previously, then if you just train a class, like a 1,000-way classifier or something, and you see a new image class, it's not necessarily going to actually correspond to any of those 1,000 things, and the classifier may do unexpected things in that case, because it's sort of like an undefined behavior. That said, you can still use the embedding of a supervised classifier and do like nearest neighbors in that embedding. And that kind of approach more resembles these kind of meta-learning approaches here. And then of course, if the test classes that you have lie within the kind of classes that you see during training, then it definitely makes sense to use supervised learning rather than to use meta-learning. It's really when you have new classes. Yeah?
In that scenario, when you have new classes, wouldn't that violate like some of the like
like distribution assumptions that we made in the beginning of like last week, where you assume like the test, amount of tests and like the training data come from the same distribution?
Yeah, so the question is, when we introduce new classes, are we violating this kind of assumption that the training and test tasks come from the same distribution? It's a little bit difficult to say, actually. In some ways, as long as the classes themselves are coming from the same distribution and you have enough training classes, then you should be fine. You should be able to generalize to new classes. It becomes more of a problem if you have a small number of classes, because then it's like less clear what is in distribution or not. Okay, so one of the things you can note here is, unlike the Siamese networks, meta-train time and meta-test time match. So we're doing Endway classification both during meta-training and during meta-testing. Okay, so in terms of the algorithm, we could take the algorithm that we learned before from the black box approach, where we sample tasks, sample data sets, and then learn from the training data. And what changes is these two steps right here. So instead of computing some parameters for solving that task, we're instead going to be computing labels according to nearest neighbors in some embedding space. And as we kind of talked about very briefly, because we're essentially integrating out these parameters phi, we're not actually representing phi directly. This is why it's referred to as a non-parametric approach, is that we don't have parameters. And then in terms of actually updating in the meta-learning process, we update the parameters of our embedding function such that the nearest neighbors process produces the correct answer. Cool. So from there, yeah.
Why is it a sum of like a bar map?
So it's a sum in the sense that usually your classifier outputs like a distribution over classes, and then you'd use like a cross entropy loss or something like that to compare the distributions. In terms of actually predicting the label, I guess I should maybe represent that as like a p over y test rather than y test directly.
Okay.
And then, yeah, in terms of practice, you're actually using this, you would actually take the argmax rather than a sum.
Okay.
Cool. So now one thing that came up before is like, what if you have more than one shot or more than one training example? In both of the previous approaches, we were treating each example from a class completely independently. And so if we had like 5 examples from the same class, we would just be comparing to each of those 5 images and not doing any sort of kind of aggregation of the information. And so one last thing that we can do to make this approach better is instead of performing comparisons independently to all of the examples within a class, you can actually try to aggregate class information into a single embedding of that particular class. And so this is essentially what that looks like, is instead of doing comparisons to all of these green data points and all the blue data points and all the orange data points independently, what you'll try to do is aggregate in some embedding space by just averaging the embeddings of those examples, and then take the nearest neighbors to the kind of class embeddings rather than the example embeddings. So in some ways, this looks a little bit like k-means in a sense. It's not actually an unsupervised procedure. It's still a kind of a meta-training procedure, but we're going to be computing these prototypes or these kind of cluster centers and then comparing to those prototypes. And so mathematically what this looks like is we will be computing these prototypes, which are just taking all of the examples for a particular class and averaging the embedding of that class. And then once we have these prototypes, we will then do, we'll kind of compare using some distance function. It could be by multiplication. It could be like an L2 distance function or something like that. And then we could exponentiate and normalize to get a distribution. And so D here corresponds to, it could be Euclidean distance or cosine distance. Well, measuring the distance between f of x, which is the white dot, to each of the c's, and then comparing the distances between the two different classes. Okay. Yeah.
I'm wondering if that's always the correct assumption that we
the classes, two different classes dogs, but they're different breeds of dogs, like in the class, this condenses it into a dog. Why is this like better?
Yeah, so the question is like, in some cases, maybe your classes are somewhat heterogeneous, like maybe you have different breeds of dogs and maybe you shouldn't actually aggregate by averaging, or maybe you shouldn't have a single prototype per class. There's kind of a couple answers here. I guess the first answer is that in some cases it may not actually be a good idea to have a single prototype, and I'll mention an approach in a couple slides that actually has multiple prototypes per class. And the second answer is that these embeddings are learned and they're high dimensional, and what the network can do is it can learn a representation that tries to kind of really get the essence of a dog, for example, and collapse out things that don't correspond to a dog, and potentially learn a representation space in which like the variants of dogs are invariant. And so even in cases where you have heterogeneous classes, oftentimes this approach still works pretty well, especially if you give the embedding flexibility. That said, I'll mention an approach that doesn't do that. Yeah.
And would you want the network actually to learn what a dog is? Because in the case maybe you're given like class where there is no dog and you still have to do the classification process.
Yeah, I guess.
So wouldn't you want filters that somehow like find textual similarity between pictures more than actually like classifying things? Yeah,
essentially, I guess what I meant by dog is that you essentially want it to be invariant to things that are class agnostic and push together things that are kind of representative of a class. It could be dog features. I mean, in general, it should be like more like textural, more general things than something specifically with respect to a dog, so that you can generalize to new classes. Okay, so to summarize these non-parametric methods, we saw 3 versions of it: Siamese networks, matching networks, and prototypical networks. This is essentially the evolution of these methods, and I think that prototypical networks is probably, it is somewhat, I don't know, in my opinion, it's at least one of the kind of methods that keeps all the simplicity of these methods, and it also works very well. I think that it's probably the best of these approaches, and it's also one of the simplest methods. Essentially, all of these approaches correspond to doing some form of embedding and then doing nearest neighbors in that embedding space. They just do this in slightly different ways. And so one challenge that does come up is that you might need to reason about more complex representations or relationships between data points. And so there are approaches that are a little bit more complex than these methods, but that try to address more challenging few-shot learning problems. So for example, one thing that you could do is instead of using like cosine distance, or instead of using Euclidean distance, what you could do is you could actually try to learn a distance function. And so essentially what this approach is doing is it's learning these features just like in prototypical networks, but also essentially learning a distance function between classes rather than using a fixed distance function. Another approach, like I've mentioned before, is to learn kind of a mixture of prototypes rather than just a single prototype per class. And then lastly, another more complex approach that you can do is to try to do some sort of message passing on the embeddings rather than just doing a simple comparison. Cool, so that's a summary of non-parametric methods. Are there any more questions before I go through a case study? Cool, okay, so in last year's version of the course, I went through a case study that was looking at dermatological image classification. I just wanted to briefly mention it because it's a pretty cool paper. And if you're interested in things related to like medical imaging or diagnosis and that sort of thing, or long-tail distributions, this is a cool paper. And it kind of adapted prototypical networks to this particular problem. The case study that I want to go through this year is actually a project that we worked on earlier this year, where we actually deployed the algorithm to kind of in a live application, which I think is not always, maybe more rare in terms of things that are so on the edge of research. Okay, so the problem that we have here is that we want to give feedback to students. And as a very concrete example, Stanford offered this free Intro to CS course to more than 12,000 students. And we wanted to be able to give feedback to the students on a diagnostic exam that they took in the course. And their submissions corresponded to open-ended Python code. And we estimated that it would take about 8 months of human labor to give feedback to all of the students in the course. And this isn't just a problem for this particular course. This is really a problem for any sort of like online education where we want to scale feedback to large numbers of students. So this is really what the problem looks like, is we have some Python code that the student wrote, and we want to be able to identify some misconceptions that they had. And we can frame this as a classification problem where we, or really a multi-class binary classification problem where we essentially classify whether they had a certain misconception or not. And this is using the same rubrics that instructors at Stanford use to give feedback, kind of like grade scope style rubrics. This is a hard problem. In general, also just a hard problem for machine learning because you don't have that much annotation. It takes a lot of expertise and a lot of work to give feedback. This data tends up being very long-tailed in that you can solve the same problem in many different ways. And also, instructors are constantly editing assignments and solutions, editing assignments and exams, and as a result, the solutions and the questions and the feedback look very different from year to year. Okay, so how might we frame this as a med-learning problem? Does anyone have any thoughts or ideas? Yeah?
You train on past exams, or even just a subset of current exams.
Yeah, so you could meta-train on past exams, and then what do you do at meta-test time? Any thoughts? Yeah?
Treat each assignment as a separate task. So in your X number, n number of years and 3 tasks per year, so you have 3 number of tasks. And other than you can take like a 2 tasks per year as you test training and 1 task for the testing.
Cool. So yeah, you could essentially have different assignments be different tasks, and you can like meta-train across that. And then when you're given a new assignment at meta-test time, what happens then? When you're given a new assignment at meta-test time, what happens at that point? So you could just run the algorithm, although we need to somehow adapt the model in some way. Yeah?
Could you just feed the actual code into the model and it would assume there's a few different common solutions to each problem, so then you'd be able to classify them and compare the student solution in some sort of embedded space.
So you can embed the code and then do some compare it to common solutions, and then where do those common solutions come from?
Well, I assume we have like a meta-training set of maybe one function is used commonly to solve this problem, but maybe a few students do it another way, and so that creates like distinct groups of solution types.
Yeah. So you could essentially have different solution types to different problems. Did you have something to add?
I'm still thinking about it. Do I can train it right now?
The person behind you?
Maybe like how it does well through like
Yeah, so when you have a new assignment, you can have the instructor label a few examples and then use that as your kind of training data set for the test assignment. Cool, so that's essentially what it will look like. So for meta training, we have 8 exams from Intro CS course, CS106. And each student, this is fully labeled, the students get feedback via the rubric. Getting into the details a little bit, each rubric has items, and each item has several options. And so an example of a rubric looks like this, where the misconception has to do with string insertion, and then you have different options with respect to this particular concept. And then what we're actually going to do is, instead of treating different assignments as tasks, we're going to actually treat each of these rubric options as different tasks. And so this is a binary classification task, this is a binary classification task, and so forth. And we'll essentially get tasks for each one of these rubric options, and we'll have 4 tasks for this, and then for another rubric item, we'll have some number of additional tasks, and so on and so forth. Cool. And then this is the meta-training process. And what we'll do is we will use essentially prototypical networks. And our model will take as input a sequence of Python code tokens. And we'll use a stack transformer model to essentially take the code and embed that into a fixed dimensional embedding. And then run prototypical networks. And then at meta test time, we will have some solution, actually a lot of solutions. We'll label a few of them and use that to generate the prototypes for true and for false for each rubric option. Yeah.
So on the previous slide, we're treating each rubric item as a different task. Don't we still need some sort of grouping over the tasks to say that these 4 tasks don't fall under this rubric, or are you just treating it completely separately?
In this case, we did actually treat it completely separately. There's one thing that we did that I'll mention soon that makes them slightly less separate, but because like these 2 things can both be true, for example, and so as a result, we need to basically like do a classification problem here and solve this classification problem. And I'll talk a little bit about how we can give the model a little bit more information. Yeah.
Doesn't it kind of mess around with like the distribution assumptions, because here like usually we assume that we sample tasks IID, but here like when we sample, for example, one rubric item under the string insertion rubric, then it's likely that the other tasks would also be sampled in the sense like
Yeah, so the question is, does this kind of break the IID assumption in terms of tasks? When we sample tasks, we don't always sample like all 4 of these tasks from this rubric item. We essentially sample IID from the distribution of rubrics or of questions, and then over the distribution of items, and then over the distribution of options. And we try to sample do that sort of sampling in an independent fashion. Okay, so this is kind of the V0 for what we tried for this problem. And we found that actually applying this out of the box didn't work very well. And that attention isn't quite all you need to solve the problem. So there were a couple tricks that we found to be pretty helpful, especially because we didn't have that much meta-training data. So the first trick was that we can, instead of only using tasks from the meta-trained data set, we can augment the rubric tasks with self-supervised tasks. So we could have a task that corresponds to predicting the compilation error that happens. We can also do this sort of masked language modeling kinds of tasks as well. The second trick is to incorporate side information into the model. So if you only have a few examples of positive and negative examples for a particular rubric option, it can actually be somewhat ambiguous what you're trying to classify on. And so we can give it side information that corresponds to the name of the rubric option as well as the text of the question. And this essentially gives the model a little bit more information with respect to like how it's supposed to be giving feedback to the student and what this rubric option corresponds to. And essentially we'll just kind of prepend the side information into the transformer model. And so this is kind of answering the question before about treating these completely independently. Because of the side information isn't quite as independent. Then the last thing we found to be super helpful is to pre-train on unlabeled Python code. And the way this works is there are some great databases or data sets that have a bunch of Python code, and you can run a model like BERT on that code to get some pre-trained embeddings. And we do this pre-training before doing the meta-training process. Okay, so the full model looks something like this, where we have the code that the student wrote. We also have the question text and the rubric text. We pass all of this through a transformer model to get an embedding of that solution with respect to that question and rubric option. And then we do that for all of the positive examples for that rubric option and average to get an embedding for positive, as well as average across the solutions that were negative for that particular rubric option. And then we get a prototype both for positive and for negative, and then we can compare new student solutions to those 2 prototypes. Okay. Cool. So I guess when we approached this problem, we didn't actually it's a pretty difficult problem to give feedback to students. We didn't really understand. We didn't have like super high expectations with respect to how well it would work. It turned out to actually work pretty well. So using the kind of prototypical networks outperforms the supervised learning method by around 8 to 17%, which is pretty significant. We also see that in the case where you have a held out rubric, you can actually do better than a human TA in terms of accuracy or precision. You're more accurate. In the case where you have a held out exam entirely, there's still room for improvement, so we're still about 8% worse than a human TA. But still, like 74% accuracy is, in my opinion, actually pretty good. And then lastly, we also deployed this model to the Code in Place course that I mentioned previously. So the students took the diagnostic on May 10th. We need to actually give the feedback to the students in some way. And so Chris designed this interface. We paired the rubric option with some text that described the feedback for that rubric option. This text was written by a human, but the classification problem was done by the meta learner. The students evaluated the feedback. We also used syntax highlighting to try to show them where the error was. And then lastly, it's worth mentioning that if there are syntax errors anywhere in the code, that means that you can't really use unit testing to actually give feedback to the students. And that's why having like models that take as input the raw text or the raw Python code is pretty helpful. And so lastly, in kind of a blind randomized trial, humans gave feedback on around 1,000 of the student solutions. This is used in the support set. Because we actually had a decent amount of data here, we also fine-tuned the model as well. And then the model gave feedback on the remaining 15,000 examples, and around 2,000 of them could be auto-graded. And so what we found is that in both cases, actually, the human and the machine learning model were actually giving pretty good feedback. The students were agreeing with the feedback from the model 97.9% of the time, and it was agreeing with the human. They were agreeing with the human feedback 96.7% of the time. Now, you could agree with things, but not have those things not actually be useful. So we can also ask them if they think it's useful, and they said it was. They rated it as being useful with like a score of 4.6 out of 5. Cool. And then last week, we also checked for kind of signs of bias by demographics, which is usually a good thing to do with machine learning systems. And we didn't see any signs of bias in terms of the most represented genders and countries in the data set. Cool, so hopefully that gives you a sense for how we can try to formulate problems in the context of meta learning, and also an example of how these algorithms might actually be deployed in real world scenarios. Cool. And that was actually also a specific case of deploying a non-parametric method. Now let's go through some properties of meta learning algorithms and try to compare the different kinds of approaches. Cool, so we've talked about 3 classes of approaches. And if you think about these from the standpoint of meta learning, like having this computation graph and optimizing that computation graph end to end, we can think of black box models as, we can essentially view all of them as a computation graph that takes as input training data and a test example and produces the corresponding label. Black box methods treat the computation graph in a like fully black box way. Optimization-based methods embed a gradient descent procedure or something like that into that computation graph. And then lastly, non-parametric approaches can also be viewed as having this particular kind of computation graph. And that computation graph is something that embeds nearest neighbors, or something like nearest neighbors to prototypes within that computation graph, where we are comparing the test example to these prototypes, and these prototypes are computed from the training set using the following equation. So essentially, in many ways, all of these methods are doing the same thing. It's just different forms of computation graphs to embed structure into the meta learning process. Now, I can also note again that you can mix and match different components of this. And so in many ways, I think that these are really the kind of the 3 kind of base classes of approaches, but there isn't a hard line in between these kinds of approaches. So you can have methods that are like sort of hybrid methods that For example, condition on the data and also run gradient descent on the data. Methods that compute some embedding, like the embeddings that we see in non-parametric approaches, and then do gradient descent on that embedding, as well as approaches that do something like MAML, but initialize the last layer as prototypical networks during meta-training. So there isn't really kind of the separation between these kinds of approaches is very blurred. And there are many approaches that are don't cleanly fall into any one of these three approaches. Yeah.
I know some already has this like RL squared. How do you classify that kind of random?
Yeah, so the question is for early approaches like RL squared, which is a meta-RL algorithm that we'll talk about in a couple lectures, how would you classify that? RL squared is basically just an LSTM, and so I would classify it under the black box approaches because it takes as input the data and passes it through a recurrent network. Cool. So that was the kind of computation graph perspective. Another way that we can think about these classes of approaches is their kind of algorithmic properties. And I think that this is useful for thinking about when you might use one approach versus another. So one algorithmic property that we might want is for it to be very expressive. And what I mean by expressive is the ability to represent a wide range of different learning procedures. And this can be useful because in some scenarios, we may have a lot of meta-training data and we want to learn a very specific or a very good learning procedure. And if we want to learn a very good procedure from a lot of data, then we should be able to represent many different learning procedures. Another property that we should care about is what I'll refer to as consistency. And what I mean by consistency is that the learning procedure that you get, ideally, it would monotonically improve as you get more data, or at least monotonically improve in expectation. And essentially, I like to use the term consistency because in statistics, consistency refers to as you get more data, your estimator will converge to the true estimator. And so in this case, a learned learning procedure is kind of guaranteed to be consistent if it improves expectation as you get more and more data, converges to the right answer. And this is important because it potentially reduces the reliance on the meta-training tasks. And so if you don't have a lot of meta-training tasks, or maybe you have a domain shift between meta-training and meta-test time, if you guarantee that your learning procedure is consistent, then you'll at least be able to improve as you get more data on the test task. And so this potentially means that you might get better OOD performance, especially if you have a lot of data of your test task. And you can recall that last week we kind of showed these curves that showed kind of OOD performance of different algorithms, and we see a pretty big difference between different approaches. Okay, so these two properties are important for a lot of different applications. And if we think about these three classes of approaches, we can think about them in terms of those properties. So black box methods have complete expressive power, but they aren't guaranteed to be consistent. As you pass more data into the recurrent neural network, it may not continue to improve. Optimization-based approaches are consistent because it essentially reduces the running gradient descent at meta-test time, and so in expectation, you will improve. If you have a very deep network, it is very expressive, but you do need a fairly large model to do that. And this is specific to supervised learning settings. When we move to RL settings, the expressive power is actually somewhat reduced. And then lastly, for non-parametric methods, they are quite expressive for most architectures. And under certain conditions, they will be consistent as you get more data to compare to. Okay, so these are a couple different ways of thinking about these algorithms. There are some other pros and cons as well that I'll go through. So black box methods are easy to combine with a variety of different learning problems, but it leads to a challenging optimization and is often data inefficient. For optimization-based approaches, we also talked about how this has a kind of positive inductive bias at the start of meta-learning, which means that it can be easier to optimize. It also handles varying and large K pretty well. You can run gradient descent even with a very large amount of data. And it's model agnostic. The downside is that you get this second order optimization, and this can mean that it can be compute and memory intensive if you have a very large optimization process. And then for non-parametric methods, one thing that's quite nice about them is that unlike something that's doing like gradient descent in the inner loop, it's an entirely feed-forward process. Like doing nearest neighbors, for example, is entirely feed-forward. And this means that they are usually computationally very fast and also pretty easy to optimize. In practice, people have found that these algorithms sometimes don't generalize well to varying k. And of course, they don't scale well to very large k because you need to do k comparisons or n times k comparisons. And then lastly, so far these methods are limited to classification. So overall, I think that if you have a classification problem, this class of methods is really great. If you have a regression problem, for example, these approaches are less applicable. And then lastly, I think that well-tuned versions of these approaches generally perform fairly comparably on a lot of the few-shot learning benchmarks. I think that this likely says more about the benchmarks than the methods themselves. And ultimately, what you end up using will probably depend on your use case. But hopefully this gives you a sense for the kinds of things you should be thinking about when deciding which method to use. Yeah?
I may have missed why the non-parametric approach is not super effective when k-means.
Yeah, that's a good question. I think this is more of an empirical observation than anything kind of theoretically about them. I think that it may have to do with, like in prototypical networks, for example, like averaging a lot of things may be difficult, especially if those different things are somewhat heterogeneous, like in different parts of the space. Then averaging them may lead to kind of weird behavior. That's some of my intuition, but I'm not sure if that's exactly what's going on or causing them to have less performance when you have varying k.
So your average might be skewed, is what you're saying.
Yeah, your average might be skewed, exactly. Cool. Yeah.
And on that topic, what would be a regression task for you to try to learn? Like I could see it maybe with robotics if you have like 5 different robotic arms, and then you're learning like, hey, okay, if I want to get into one pose, like what's my output? And then you extract it to like what we can add, and that would work. But do you have like a good example?
Yeah, so you're asking like what are examples of regression problems in meta learning? Yeah. Yeah, so we'll go through a couple of example problems at the very end, but some examples are things like pose prediction, like predicting the orientation of objects. If you like want to control a robot and it has continuous action spaces. One other example that we had in the mammal paper that I think is a nice toy example for playing with algorithms is one where different tasks correspond to different sinusoid curves, and you want to predict like the if you want to predict essentially the value of the sinusoid curve for a particular input. This is actually a nice toy problem, especially if you want to like try out new approaches and so forth. Those are some examples. I mean, I think that there's also like a lot of machine learning problems in general that have more continuous output spaces as well. Okay, and then one other kind of property that I'll mention is what I'll refer to as uncertainty awareness. And in particular, if you have a very small number of examples, it may be that your task isn't actually like fully defined in some ways. It may actually be unclear what the correct behavior is. And it's nice if our algorithms can reason about that ambiguity and tell us when they aren't sure about the task, versus just trying to guess something without saying whether they're unsure or not. This is something that's useful in machine learning in general. And it's also useful in settings where you want to do some form of active learning, where the algorithm should ask for more data, for example. Or maybe you want to get calibrated uncertainty estimates, or maybe in reinforcement learning, you want to be able to efficiently explore the space and find parts of the state space that will help you reduce ambiguity. And it also, I guess, it's nice to derive approaches that are kind of based on like Bayesian inference and stuff like that. And it can be somewhat satisfying to kind of explain the framework within the context of that kind of language. And so we'll essentially discuss this a lot on Monday next week. And it's not just going to be about having algorithms reason about ambiguity, it's also going to be about deriving these algorithms and thinking about different tasks from the standpoint of kind of Bayesian graphical models. Cool. Any questions on the algorithms before I move on to some applications? Yeah.
I mentioned some conditions, but for consistency in non-parametric models. Are they conditioned on a model structure or data?
So you're asking, are these properties?
When you talked about non-parametric, you mentioned it being consistent under certain conditions. Are these conditions on a model structure or data?
Yeah, so I think this is consistent under certain conditions. Yeah, so it's going to have to do with the model structure. If your data is drawn IID, then I think that you're set. But if your model structure, for example, like collapses down information, like essentially if your embedding discards information about the image or discards important information about the image, then you'll no longer be consistent because as you get more data, even if you get more and more data, there might be parts of that embedding space that are just like, should be there but aren't in that embedding space. Yeah, so that's it's essentially about the kind of representation that it ends up learning. Yeah.
Is non-parametric method the most robust way to domain shift forward?
Yeah, so the question is, are non-parametric methods the most robust to domain shift? I think that actually optimization based on non-parametric both tend to be a lot more robust than black box methods. I haven't seen any kind of detailed empirical analysis on which of the two tend to be more robust. If I were to guess, I would think that non-parametric methods are slightly more robust just because they're simpler to train, and things that are kind of simpler to train often might kind of overfit a little bit less to the meta-training data. Cool. So now let's run through a couple more applications. I'll run through these pretty quickly, but these should just give you a sense for some of the different ways that people have applied meta-learning. And we'll also end on a note that I think is a more general note that I think is useful for thinking about new kinds of applications. So one application in the domain of robotics is, say we want a robot to be able to place an object into a container, and we want to be able to place it into a container, even for containers and objects that it hasn't seen before. What we can do is we can give it demonstrations of placing objects into containers for a wide variety of objects. And then at meta test time, our training data will be a video of a human placing into a particular container. And our query data or our test data for each task will correspond to a teleoperated demonstration of solving that task. And this is going to be an optimization-based model, and it's going to correspond to MAML with a learned inner loss function. And what you get is something like this, where at meta test time, you give it a video of placing an object into a new container, and then the robot adapts its policy using that video of a human, and then gets a policy that acts like this. And as long as you have each task essentially corresponds to dropping, this task corresponds to dropping in the red bowl for different positions of the objects and the distractors. Another example is predicting the properties of different molecules. This is potentially useful in drug discovery problems. Different tasks correspond to predicting properties and activities of different molecules. And dtrain and dtest will correspond to different instances of those molecules. In this case, they used optimization-based approaches, and they compared 3 different approaches, which is MAML, first-order MAML, and almost no inner loop, which essentially just does MAML on the last layer of the model. And they used a gated graph neural network as the base model with MAML. And what they found is that if you do things like k-nearest neighbors or fine-tuning on top of a model, that doesn't perform as well as using meta-training on the molecules they had. Another example, this is a regression example like the first robotics example. You want to be able to predict human motion into the future. And different tasks are going to correspond to different human users and different kinds of motions. And dtrain will correspond to the past k time steps of motion, and dtest will correspond to the kind of future time steps of motion. They use a kind of a hybrid of an optimization-based approach and a black box approach. And in particular, they use MAML with this additional learned update rule. And their base model was a recurrent neural network because it needs to take as input the previous time steps of motion. This is kind of what their model looks like, whereas it kind of is adapting to the previous time steps of motion and then predicting the blue figures into the future. And then here's kind of a snapshot of the results, which they find that kind of doing some form of transfer learning or learning from scratch doesn't perform as well as their meta-learning process. Yeah.
So going back a couple slides to the imitation learning example, MAML kind of needs some sort of reward signal in that case because it's not like a supervised task.
Yeah.
How do you perform the inner loop in that sense?
Yeah, so this is a kind of a more advanced example, and essentially what it looks like is the one thing that you might notice is that the training set and the test set are actually a little bit different. One thing that you could do instead of having it be a video of a human is just to use a teleoperated demonstration. And in that case, you can just use an imitation learning loss as your inner learning objective. And so kind of what that would look like is something like where you're optimizing for the parameters of your policy such that this is your outer loss function. This is your inner loss function. This is your training demo, and then you also have your test demo. This is over all of your training tasks. And so what you can do is if you have a kind of both the demo in the inner loop and the outer loop, then you can use like an imitation learning loss function, which essentially just corresponds to like something like mean squared error between the true action and the predicted action for a given state. Now, if this is like a video of a human, then you don't actually have the actions. And so one cool thing that you could do is instead of having this be like an imitation learning loss function, what we do instead is we actually learn a loss function. And so we actually have like parameters in this loss function, and we meta-train both the initialization as well as the parameters of this loss function. Cool. And so if you're in scenarios where you actually don't have good label signal in your training set, you can actually do something like this. Cool. So we looked at the human motion prediction example. And then one more application or example that I'll mention is language modeling. And so many of you might be familiar with GPT-3. This can also be viewed as a meta-learner or a few-shot learner. And here the tasks are actually pretty diverse. They have tasks like spelling correction, simple math problems, translating between languages, and a variety of others. They're all represented as these language generation problems where dtrain corresponds to a sequence of characters and dtest corresponds to the following sequence of characters. So for example, you can give it some examples of solving math problems and then ask it to solve more math problems for you. You can give it examples of correcting spelling and then ask it to correct spelling of more things, and so forth. The model that they use is a very large transformer model, and so you can think of it essentially as a black box meta-learner. And there are some cool examples of what it can do. So you can give it, essentially the gray text corresponds to dtrain, and then the black corresponds to the generation from the model. And so you can give it an example of a new word that it should learn, and then ask it to use that word in a sentence, and then it can generate an example of using that word in the sentence. You can also ask it to edit language, so to say like poor English and good English, give it, in this case, 1, 2, 3, 4 examples of that, and then ask it to ask it to generate, actually no, sorry, 3 examples. Yeah, three examples up to here, then give it another poor English input, and then ask it to produce the corresponding output. Here's another kind of example of correcting the English. Yeah.
To clarify, this doesn't really update the model parameters at the test time, does it?
Yeah, so essentially, the prompts here essentially correspond to the kind of training data for the example. And it's essentially like a black box meta learner where it's the version of a black box meta learner where you're outputting like some hidden state or something like that rather than outputting like a full set of parameters. And kind of similar to the kind of black box meta learners that you're implementing in homework 1. Okay, and so one closing note that I'd like to mention that we saw actually in a lot of these examples is that dtrain and dtest don't actually need to be sampled independently from the data for a task. And this is pretty cool because this means that you can actually kind of tweak the meta training process in a lot of different ways. You could have dtrain have like noisy labels and dtest have clean labels and essentially learn how to learn from noisy labels. Essentially get an optimizer that can learn well from the noisy labels. Dtrain could also be like weakly supervised, kind of like this example right here, where you actually learned a loss function. It could also have some domain shift. So you could have, you could try to learn from data from a different domain such that it produces a model that works well in some target domain. And so this is what would happen during meta training time, and then at meta test time, you could give it data sets that have noisy labels or weak supervision and so forth, and get models kind of like the ones that you want. Yeah?
So essentially, you can just need that the training distribution. But have the training distribution be harder than the testing?
Right, you're asking, do we need to have training to necessarily be harder than testing? Essentially, what's really important is that the desired behavior of the model is represented in dtest, because this is what's going to be used to like actually train the model to get some desired behavior. And then dtrain should represent the kinds of data that you're going to give it at meta test time. And so if you want it to be able to learn from noisy labels at meta test time, then it's good to meta train it to be able to handle noisy labels. You could also try to have like meta train it on harder tasks, like meta train it on the ability to learn from noisy labels, and maybe that would make it also do better at clean labels because it's just a harder task. But that wouldn't, kind of more of what I'm trying to convey here is you can actually do some cool things with the meta learner that actually trains it to be able to handle different kinds of learning problems. Cool. So to recap what we talked about today, we talked about quite a lot of things. Non-parametric few-shot learning approaches, which learn to do these nearest neighbor matching queries. We talked about properties of meta-learning algorithms and compared different approaches. And then we also looked at a few applications. And then, yeah, to end, a few reminders. Homework 1 is due on Wednesday. Also, please fill out the project survey by Wednesday. And the project proposals will be due next week.